All right, so let's see how we actually do this with some functions. Let's work on those. Okay, so remember that the natural log is the inverse operation of e to the x. And so what that means is, if we look at this, the input of the e to the exponential function is the output of the natural log function. And the output of the natural log function of the natural exponent function is the input of the natural log function. So it's basically we're switching the output and the input. So basically, I like to write it this way. So if I have some base to the x equals y, then remember our base stays the same. So this is log base b, and then our output becomes our input. So our y goes here, and our input becomes our output. Okay? So our output becomes our input, input becomes our output. All right? And we could go the other way. If we had log base b of y equals x, then our base stays the same. I'm going to put that here. Our base stays the same. And then our input becomes our output. And our output becomes our input. Okay? So that's how we switch them back and forth. So in this case, let's look down here. 3 to the 4th equals 81. Well, 81 is our output, and 4 is our input, right? 4 is what we put into the function, and out spits 81. So our base stays the same. So we still have log base 3. And we take our output. It becomes our input, 81. And our input, which was 4, becomes our output. There we go. That's it. So for this one, remember this is base stays the same, so we've log base e. Our output becomes our input, so that's a 1. And our input becomes our output, so that's a 0. And what is log base e? Well, log base e is the natural log. So the natural log of 1 is 0. Okay? Now this next one, it's the other way around. So it's asking us to go from a log to an exponential. So again, let's keep our base the same. So our base is still 10, because when you see log without a base written, it's just 10. And so then our input becomes our output. So we have 0.1 here. And then our output becomes our input. So we put -1 there. And that makes sense, right? Because 10 to the -1 is 0.1. It's 1 over 10. So, since e to the 0 equals 1, ln of 1 is 0. And since e to the 1 is e, ln of e is 1, because, our input becomes our output. Okay? So because the natural exponential function and the natural logarithmic function are inverses, in other words, ln and e are inverses of each other, they kind of cancel each other out. And I don't like to say cancel out because it means, people start just willy-nilly, crossing stuff out. But it's kind of what they do. They undo each other, right? So the e undoes the ln, and the ln undoes the e. So if I have some number, n, and I take e and raise it to the n power, and then I take the ln of that, guess what? I get all the way back just to n. So in these examples below, you'll see when I do these two inverse operations on this number, I just get out the original number back. Same here, I get 3x back out. And then if I look at this one, now 10 to some exponent is the inverse operation of log base 10. So I still end up just getting out 2 because these kind of undo each other. And then log base 2 and 2, the exponential function with 2 as a base, undo each other. So all I have left is x squared. So there are some properties of logs that I want to talk about. Now, the first thing I actually really want to talk about, though, is that functions do not distribute. Okay, And what I mean by that is, how many times have you seen this happen? A plus b squared equals a squared plus b squared. Is that true? No, absolutely not. It is never true. Well, yeah, it's not true, okay? It's not true. Functions do not distribute, and logs are functions. In other words, if I have the ln of two numbers added together, I cannot, absolutely cannot just say, well, that just equals the ln of a plus the ln of b. They do not, absolutely do not equal each other, okay? Super important to remember. Functions do not distribute. So what are some properties of logs, though? Well, if I have two functions, or two numbers multiplied together, I can split their natural log into two separate ones, just like that, adding together. If I have two numbers dividing, I can split them and just subtract the natural log of the first one minus the natural log of the second one. And then this one is the one we use in calculus like all the time. We use it so much. It's so awesome, okay? And I don't know that we use it in Calc 1 as much as we use it in all the other calculuses, but we use it so much because it helps us get an exponent out of the exponent, which is so cool. Okay, so if I have ln of a to the n, this n can come right down in front. And so then I get n ln of a. So it just like takes that exponent out of the exponent and brings it down front. It's super cool. I know, like geeky math cool, but still cool. Okay, so if I have ln of 5 divided by 8, remember this is the same as ln of 5 minus ln of 8. That's really it. And that makes it so much easier to derive or integrate because now it's in two separate forms. Okay, so what about this one? You might not understand maybe what's going on here first, but let's go ahead and rewrite it in as a rational exponent to the 1/3. And now we can use the properties of exponents, or of natural log, or any log, to bring that 1/3 in front, and we have 1/3 ln of x squared plus 1. Now I want to remind you, I forgot to say this a minute ago, that this works for all bases of log. So log base e, which is ln, or log base 10, or log base 2, or log base whatever. Any base, any log with any base, these work for. So if this had said log base 5 of the exact same thing, you could have done the exact same process. You could have brought the 1/3 down, then it would still be log base 5 of x squared plus 1. Okay, so whatever log it is, even if it's natural log or other logs, it all works. Okay, let me see where we're at now. Oh yeah, so then we're going to condense these into a single log. So the very first thing I see is I see this -3 out front, which tells me that can probably go up into an exponent, and this can probably go up. We can undo what we just did a minute ago, so I can bring this and make it an exponent, and I can bring the 5 and make it an exponent. So now I have the natural log of x to the -3 plus the natural log of y to the 5th. Okay, now we have another property of logs that says when I have two logs added together, it's really like I'm multiplying those two inputs. So now I have the natural log of x to the -3rd times y to the 5th. Okay, and when I multiply those together, I have ln of y to the 5th over x to the 3rd. Now either one of these is fine. They're the same thing. It just depends on what we're needing to do with them. Okay. This next one has a few things going on, but again, the first thing I see is I see some numbers in front of the natural log, which tells me I'm probably going to bring them up into the exponent. So let's go ahead and try that. So I bring that 1/2 into an exponent. I have the natural log of x plus 1 and minus the natural log of y to the 3rd. Now you could have brought up a -3 and it would work either way, but I'm just bringing up the 3. Okay. So then I notice that these are adding together. So I'm going to have the natural log of x to the 1/2 times the input of the other function. Okay, so that's that property of logs. And then since this one is subtracting, then I can just divide by y cubed, and I can just take the natural log of the entire thing. And then we're done. Okay, here are a couple ones we're solving for x. Okay, so the first thing we want to do is we want to get the exponential all by itself, because remember, logs don't distribute, so I can't just take the natural log of this side, because it won't be the natural log of e to the x plus the natural log of 6. That doesn't work, right? Okay, so we have to get that e to the x all by itself so that we can then, start getting that exponent out. So this is y minus 6 equals e to the 2x minus 5. Now, if I take the natural log of both sides, that e will be undone, right? It'll undo the e. So let's do that. Let's take the natural log of both sides. So I can just leave that like that. When I take the natural log of e to some power, these undo each other, and we end up with the natural log of y minus 6 equals 2x minus 5. Now x is still not by itself, so we're going to subtract 5 from both sides. And instead of writing it at the end, I write it at the beginning just so that it's very clear that it's not in the natural log function. Because otherwise sometimes it looks like it's part of the natural log function. And then we divide by 2. So x equals this big long mess. And there you go. Solved for x by using the natural log to get it x all by itself. Okay, now this one, we have to figure out what we want to do first. Well, we have two log base 2's, so let's go ahead and get those together and start there. So this would be log base 2 of x divided by x minus 8, because that's one of the properties of logs, and when we're subtracting we can just divide those. Okay, and now to undo log base 2, I can raise both sides. I can say 2 to this power, right? And then that undoes both of those, and what I'm left with is x over x minus 8, and then I have 2 to the third. Okay, so I'm close to done, but x is still not quite by itself, so I have x over x minus 8 equals 8. I multiply both sides by x minus 8. Those become 1, and I have x equals 8x minus 8. And then I subtract 8x from both sides. I get negative 7x equals negative 8. And in the end, I have x equals 8 sevenths. And then we're done. Just kidding, it should be 64. I knew it. I was like, man, I don't remember that number. Okay, I messed up right here. So this should be 8x minus 64. So then we end up with negative 64. So in the end, we end up with x equals 64 sevenths. Okay, that seems more like what I worked out.